Hello everyone, welcome to the GeoDict 2023 Workshop for Digital Material R&D. This year, we're going to have a closer look at modeling and property prediction of additive manufactured materials with GeoDict. At first, I would like to give you a short introduction to additive manufacturing modeling. After that, I will lay out the aims and the goals of this workshop. Then, the structure modeling for additive manufacturing with GeoDict will be shown to you. In the fourth part, we are going to have a look at the property prediction on additive manufactured models. And finally, this is followed by a short parameter study on those additive manufactured models from before. And at the last, I'm going to give a short wrap-up of the workshop. Let's head into the first part, Introduction to Additive Manufacturing Modeling. Additive manufacturing became more important the last years due to increased capability of modern additive manufacturing methods. In particular, laser sintering allows creating very delicate structures. On the right-hand side, you can see such a powder bed where a laser beam melts the material and which later on forms the structure. With additive manufacturing, also metamaterials can be efficiently manufactured. A metamaterial is a material engineered to have a property that is not found in naturally occurring materials. And metamaterials derive their properties not from the properties of the base or the bulk materials, but also from their newly designed structures. For example, heat sinks can be a very interesting application for that. Structure generation for additive manufacturing. In conventional manufacturing processes, GeoDict already offers various modules to model those manufacturing processes. For example, Fiber Geo for non-wovens or composites, Paper Geo for pulps and papers, open and closed cell forms for foam-like structures, and Grain Geo for ceramics, metals, and others. While additive manufacturing can be tackled with the Grid Geo model from GeoDict to create regular structures. In contrast to conventional manufacturing process where always some kind of randomness is underlying the fiber distribution, the length, which can be controlled in the manufacturing process, but still has some slight or larger deviations. While in additive manufacturing, you can have your grid or your lattice structures, your very regular structures modeled with the module Grid Geo from GeoDict. Let's have a look at the aims and goals of the workshop. At the end of the Digital Material R&D workshop, you will be aware of the possibilities of GeoDict for different model approaches for additive manufacturing. This includes basic analysis on those models and how to conduct a parameter study with artificial models. In part 1, we will mainly look at modeling different additive manufacturable structures. In the second part, we will have a look on what analysis can be performed. In that case, we see a pore space analysis. And in the third part, we will have a short and quick look at a parameter study. The goal of this first part is that you will know basic functionalities in GeoDict. Those are setting and changing a project folder, saving and loading structures, and also the possibilities for additive manufacturing modeling, especially with Grid Geo, triply periodic minimal surfaces, and lattice-based models. On the right-hand side, we can see such a triply periodic minimal surface. This here is a so-called square-shaped gyroid. Let's head to Geodict. For that, we open our web browser, and if you follow the setup manual you received beforehand, you are now in the same browser tab as I am. Here, this year the workshop is conducted in the cloud. This means everyone has the same machine. So please everyone, we now start our Geodict 2023 instance by clicking the Geodict icon down below in the left corner. We double click it and wait for Geodict to start. As a first step, we're going to set a project folder. For that, we go to File, choose Project Folder, and we select Project Folder. You already have all those workshop materials, but we want to create a new project folder for all our results. For that, we click on this small icon in the top right to create a new folder and give a name, for example, Workshop Project Folder. We select this folder and we click Choose. Now we changed the Geodict project folder successfully. There are also quick access available. Instead of going to File, choose Project Folder, we can right-click on the folder path here and directly select Project Folder. Or we can even open the project folder in the File Manager directly. Now we head to Model and select Grid Geo. In Grid Geo, we select Grid of Spheres, or we click Grid of Spheres and select the Grid Geo apps. In Geodict 2023, the Grid Geo app has been added for strut-based lattices and also for triply periodic minimal surfaces. We will start by creating a strut-based lattice. Strut-based lattices are grids or lattices where nodes are located at the vertices or the edges of the unit cells, or sometimes even at the cell's interior. And they are connected by slender, straight members, usually called struts or beams. Here we can see a face-centered cubic. The strut-based lattices and also the triply periodic minimal surfaces in Geodict are modeled according to this publication you can find under this digital object identifier. To model a strut-based lattice, we select Edit, and now, as a lattice type, we can choose the diamond pentamode. We change the near node diameter to 0.2, and we change the center of strut diameter to 0.4. What is very important is that we always remember to give a meaningful result file name at the top. In this case, we call it pentamode because we create a pentamode lattice type and one periodic copy because we are going to have only one unit cell. We click OK and we click Run. After a few seconds, the structure generation is done and we are greeted with a result viewer and the structure is loaded in Geodict. We select the 3D view. Now can have a 3D view at the structure. Heading to the right-hand side, there are the color and visibility settings. We click those, and we can now change the color of the different material IDs. In this case, we change it to white. We can collapse this by clicking the tab again. And at camera, we can select Show Outlines and Show Halo to have a better view of the structure. And we see that indeed this is a unit cell. The neat part about this thing is this is the minimal size of the structure where we can perform the whole analysis on. And we can also do all the analysis periodically, which means the structure repeated in each direction looks exactly the same. But first we have to change the material, because we do not want to do the simulations on a glass structure, but on a more realistic additive manufactured material structure. For that, in the top, we go to Select Constituent Materials and click it. This opens the material selector. Here we can have an access to the material database, or we can choose the materials of the material IDs present in the structure. In this case, the pore ID 0 and glass ID 1. We click on glass, and now we scroll to the top and just select aluminum AA1050. We click on it and click OK. And now aluminum is set as material for ID 1. We have to click Run to apply the changes to our structure, and we can see indeed the material was changed. Now, at strut-based lattices, we again click Edit, and we enlarge the number of periodicity cells to 2 in each direction. And we have to remember, since we changed the parameters, we do create a different structure and therefore need another result file name. We change it just to 8 periodic copies, because 2 times 2 times 2 equals 8 periodic cells. We click OK and run. Now Geodict creates the same structure as before, but with 8 unit cells instead of 1. We see indeed the structure was repeated periodically, but this also means we could perform the analysis on this structure and on the structure from before and would obtain the same results if we have selected periodic boundary conditions. But of course, doing the simulations on the single unit cell, we get faster simulation results and need less memory. The strut-based lattices offer various different options for structure generation. They are also described in our user guide, which you can find by clicking Help, and in this publication. You can have a look at our user guide, the publication, or try those lattice types on your own after the workshop with the Geodict license and the cloud version of Geodict provided. But now let's continue with a different structure type. We click on strut-based lattices and select the triply periodic minimal surfaces. Triply periodic minimal surfaces, or short TPMS, are surfaces created such that they have no self-intersecting or unfolded surfaces, and those surfaces are given by a mathematical equation. For example, such an equation could be this equation. A minimal surface means that they are locally area minimizing, similar to a film of soap minimizing its surface area. On the right-hand side, we can see such an example of a soap film, where we can see that on this spiral, the soap film will try to minimize its surface area, which in reality is physically the same as minimizing the energy. And triply periodic just means that they are repeating in each direction. For example, in nature, that would be crystalline structures. But again, because they are periodic or even triply periodic, we can calculate on small unit cells and do not need to repeat the structure in each direction to get a large representative volume element. The geodetic GeoApp for triply periodic minimal surfaces creates those minimal surfaces that can be found in the publication mentioned in Geodict under this digital object identifier. Let's start by creating a triply periodic minimal surface. We click Edit, and we start by creating a shape mode. We stay with cylindrical. The radial repetitions and angular repetitions we keep the same. The repetitions in Z direction we decrease to 4. The inner and outer radius we keep also the same. And as lattice type, we keep the gyroid. We could also have various different other lattice types, also described in the publication mentioned on the left. Or we could even select custom equation, where we can enter our own surface equation. But as I said, we stay with the gyroid. This means we will create a cylindrical gyroid. As threshold mode, we select greater, equal, and smaller equal. And we change the threshold to minus 0.5 and 0.5. Geodict will create a volume field, and this threshold will make a structure out of this volume field. The length of the structure in X, Y, and Z direction, we change the Z direction to 3.5, so that we have a simply cubic structure. And again, we will give a meaningful result file name. In this case, we are creating a cylindrical gyroid, so we call it cylindrical gyroid. We click OK, and we click Run. As mentioned before, Geodict now creates a volume field and applies a threshold to this. After the generation, we can see that the volume field and the structure are loaded in Geodict. We can disable the structure view by unchecking this small checkbox and see simply the volume field. We can then head to the volume field tab by clicking on it and have a look at the influence of the thresholds, which means we could experiment with a threshold. If we think we need a different threshold, we can experiment here and select under Edit a new threshold for structure generation. Or we can have a right click on solid volume fraction. On the currently loaded volume field, which is solid volume fraction, we can right click. And we have quite a few options in this quick access menu. Here we can also select threshold to structure. And we could directly threshold this into a structure. We do not want to do that now, but keep it in mind if you need it later on. But disabling the volume field view and enabling the structure view, we see that we have indeed a cylindrical gyroid. You can see the cylinder orientation is in that direction. But this structure is kind of smooth with no imperfections on the surface. In real manufacturing processes, the 3D printer might be very accurate, but still there are slight imperfections. And we are now going to model such imperfections with Geodict. For that, we go to Model and select Crane Geo. We click Create Cranes and select Roughen Surface. We are now going to roughen the surface to apply a surface roughness, which will make the structure more realistic. We click Edit. And now we can select between stochastic roughness and add surface grains. We stay with stochastic roughness, and as feature radius we select 50 microns, and as max distance we also select 50. But as operation we only want to add new surface grains. We can also select add and subtract, which will add grains and remove grains, but for that case we might make holes into our structure, which we do not want, so we only want to add grains. And we also want to check the connectivity, because otherwise there might be voxels floating inside the structure, which we want to prevent. What also can be done with Geodict is that in the left bottom corner, you can select this leftmost icon, Save Current Settings to File. Now we give the file a name, for example, roughened surface parameters. And we can click Save. Now the parameters we changed are saved to this GPS file. We could later on load settings from File and choose this GPS file to load the settings. This way you can save your settings, or you can send those settings to your colleagues. We click OK and we click Generate. After a minute, the surface is roughened and we can observe the results. And indeed, we now have some kind of stochastic roughness on the surface. We now want to save this roughened structure for later on. For that, we select File, and we say Save Structure As, and again, we give a meaningful name. In this case, we call it cylindrical gyroid. We click Save, and the structure is saved to the hard drive. And as the last step of this first workshop part, we again head to Model and Grid Geo, and add triply periodic minimal surfaces. We click Edit, and we create another structure. In that case, for this case, we change the shape mode to square, and we leave all the other settings as they are. But now we have to remember to change the result file name, square gyroid. We click OK, and we click Run. Again, Geodik creates a volume field, applies a threshold, and finally a structure is created. In this case, we can see that indeed in this case it is a square-shaped gyroid. Again, we would like to model surface defects. For that, we go to Model, Grain Geo, and at Roughen Surface, we click Edit. Since we did not close Geodik since the last time, or we changed the settings, the previously settings are still loaded in the Roughen Surface options. We do not want to change them, therefore we just click OK, and we click Generate. The surface of the structure was successfully roughened. And as the last step of this first part, we are again saving the structure to our hard drive. For that, we click File, Save Structure As. But in this case, it's not a cylindrical, but a square gyroid. We click Save, and now the structure has been saved to our hard drive. This concludes the first part of our workshop, and now there will be a short break of about 10 minutes, and I will see you again in 10 minutes with the second part where we will have a look at the property prediction on additive manufactured models. See you again in 10 minutes.